trying to get to impedance. So what's the next step?
We can substitute Ohm's law for IR.
All right, so this is VR over R. And I'm not sure orange is gonna show up on video there, so. Let's see how blue handles it. Oh, squared. All right, that's one thing we probably should do.
We can substitute, voltage divided by reactance.
All right, so the Ohm's law variations for all of them. So this would be VC over XC minus VL over XL squared. And then over here, this would be epsilon over Z. Now what?
Is it epsilon over Z squared? Or Z over?
Oh, yeah, that should be squared. That's what you said, right? Squared, yeah. Thank you. So after we correct our mistakes, or my mistakes, what next?
The voltages are all equal to each other.
Yes. Now it's time to get rid of stuff. All the voltages are the same, all the magnitudes of voltages are the same, so that's gonna go away. And so I'm left with 1 over Z squared is equal to 1 over R squared plus 1 over X sub C squared plus 1 over X, oops, 1 over X sub C minus 1 over X sub L, that difference squared. And so we need Z by itself officially. And so let's go with, so Z is 1 over the square root of 1 over R squared plus 1 over X sub C minus 1 over X sub L. Come on. There we go. All right, so let's do some numbers. All this is well and good. We have a formula here, but let's figure out what some of this stuff is. But for instance, how long should these phasors actually be? Is IR smaller than these, if, assuming we equate units? So what are the relative strengths here? So let's go ahead and assume 60 hertz. And you know what, let's be daring. Continental, 50 hertz. I was thinking European, but European doesn't do AC, they officially do DC, but we'll pretend in our mythical world. R is 100 ohms. inductance is 15 millihenries. Power supply, wait, no, where are we? There we go. Capacitance, 3 millifarads. And VRMS is, we'll make this 140 volts. So at time is equal to 1 second. What is V sub R, I sub R, V sub C, I sub C, epsilon, small epsilon, V sub L, I sub power supply, and I sub inductance. So what the question is asking is, imagine these spacers are zipping around 50 times a second. Thus the 50 hertz. So after 1 second, I'm asking, instead of 1, let's make it 1.2. Let's go off the integers. I'm asking, because I have lowercase letters here, I'm asking for the instantaneous values. So, we have a generic, we will assume that at time is equal to 0, the voltage of the power supply is at its max. So first off, what is the significance? I guess people are still writing down, but something to mull over while you're writing down is, what is my significance? Why do I bother even saying this?
Is that the voltage of the, what is that? Yeah.
The VRMS, root mean square. So if I took my multimeter and I stuck it into the outlet, it would read 140 if I had it on AC.
Okay.
So we got a couple things here. One, how does VRMS help us? And number two, why am I bothering telling you this? Oh, we'll actually make that 1 and make that 2. So what significance is this?
Is that the peak to peak voltage? Is that what they consider? So,
No, it depends on what you're picturing right there.
yeah. That's the maximum in when the voltage goes up and down, right?
Right.
And then the maximum at the peak.
Right, okay. So if I plotted my voltage from the power supply, that's a V, versus time, it starts out at its peak. I think that's what you're saying. So what is the significance? If you're looking at this thing's oscillating back and forth on forever, or at least the problem is. What does this tell us?
Is it the phase shift? The phase shift, does it have to do with that?
Yes, it does. Do you want to keep going, or you just leaving that up for other people to pick up?
Leaving that out.
Okay, so someone else.
I think the magnitude would affect the other voltages if it was at its max. other voltages would be affected because of Kirchhoff voltage.
It will affect others, but only through the phase shift. What is gonna actually, more important for the voltage of the others, is this number right here. Alright, so when you're doing alternating current, we have this thing oscillating back and forth. What functions oscillate back and forth? Alright, that's what this is telling us. I could do cosine, this is a cosine curve right here. I can do cosine with no phase shift, or I can do sine with a phase shift, depends upon your mood. But this is establishing the fact that the phase shift, depending upon which function you want to use, we have to use cosine or sine. They say that. There are actually other functions you can use that are far more complicated, so let's just stick with sine and cosine. You can use sine or cosine, it doesn't matter which one, just pick one. Cosine seems like it's gonna be the simplest. That's the importance of this right here. So I have this generic equation here. I should probably differentiate them. I'll just stick a sub-zero here just to differentiate my epsilons. Cosine omega t plus 0, since it's starting at the peak. The lab that you're going to do on Thursday, it won't start at the peak. At least I haven't seen it. I guess statistically it is a non-zero probability, but it's highly unlikely you'll actually start it at the peak. All right, so we need to figure out these things right here. These are the numbers. How do we find omega?
T equals 1, and then we can say that omega starts at 0, because can't we define the phase shift?
Well, the phase shift would be out here. That equals 0. The phase shift is 0.
And we know epsilon.
We don't know epsilon, so not. We can find it, but we don't know it yet. What is omega? What's the quantity? Or,
2 pi over
I'm looking for a formula right now. I'm just looking for what's the vocabulary word.
angular frequency.
Yes. Say it again.
Angular frequency.
Yes. If you said angular speed, I would kind of roll my eyes, but yeah, it acts and smells like angular speed. But angular frequency is official. All right. So the question is, how do we find angular speed? And I believe somebody was about to give me a formula.
2 pi f.
Yes. Omega equals 2 pi f, which is 2 pi times 50, which is 314.159 units.
Radians per second.
Yep. All right, so now we got omega down, epsilon sub naught. What is the magnitude of our wave here? Or how would you find it? Because I've given you this. What is root mean square? In other words, RMS. What is an RMS value? All right, let's do some calculus. Woo! Calculus. Yes. I'm going to erase some of the stuff we have written up here. I guess the derivation we don't need anymore. Don't need that. Going to keep the phasor diagram. I'm going to rewrite Z over here because I suspect we'll use that again.
Is it also 140?
It is not. So if I have a sine function, or cosine, since we're dealing with cosine here, I have a cosine function. And so this would be 2 pi over omega, so y is equal to cosine of omega t. We'll stick an amplitude in there. And hopefully a better marker. So some amplitude here, this is negative amplitude. If I want to express my voltage with a single number, what number should I pick? Probably better wording is what number is picked. So when I take my multimeter and I set it for AC voltage and I stick the probes into the outlet, it's going to give me a single number, somewhere around 120 volts. It's not the amplitude. What is that number?
The average? Is it the average?
All right, so let's think about that. If I did the average of this right here, you find the average, you add up all the numbers and divide by however many you got. What would be the average of this function?
0.
Yes. So it's not the average. So the math people had to figure out a way of dealing with this. And so what they decided to do was root mean square. Root mean square. Now the words are in the opposite order in which you do it. The first thing you do is you square it. Then you take the average, and then you take the square root. Think it should be square mean root? Yeah. It's from the French, where they put the adjectives at the end. I don't know. I'm not sure why they.
That doesn't make sense.
So, if I want to find the average of, well, first off, finding the average. So y average would be the integral of y, I guess we're first time here, y dt, over the integral of dt. That's generic finding the average from 0 to 2 pi over omega, 0 to 2 pi over omega. Classic calculus form of finding average. But because we have to square it first, we square it, then find the average, and then take the square root. That, in essence, is what we're going to do. Well, the bottom one is easy enough. I can do that integral in my head, no problem. My denominator here is 2 pi over omega. So I have a, so in essence, the trick is, or the hard part is this top integral right here, a squared cosine squared omega t dt from 0 to 2 pi over omega. My amplitude is just going to come straight out. So I get a squared integral cosine squared omega t dt. Let's just do a little substitution here. Let's let x equal omega t. And so dx is equal to omega dt. And so this becomes a squared times the integral, a squared over omega, integral cosine squared x dx. So in essence, assuming a is bigger than 1, we're squaring this, and then we'll find the average of that, and then we'll do the square root. All right, so the integral of cosine squared. Two ways of handling it. I figured we would do it the math way, but you've got a better way you want to do it. Okay. But
We can all.
that's one of the ways. Oh, actually, my books at home. The whole pandemic thing.
When you leave your book at home, you have to calculate it.
About to look it up there?
Yeah.
Okay. There's a substitution that you make, but,
Would it be one minus sine squared? But actually, that wouldn't make it.
So cosine squared plus sine squared equals one. Cosine of two theta is equal to cosine squared theta minus sine squared theta. Plugging that into here. So this is cosine squared theta minus one minus cosine squared theta. So this becomes two cosine squared theta minus one is equal to cosine of two theta. And so cosine squared theta equals one plus cosine of two theta over two. That's the substitution you would make. But Lawson's gonna look it up.
It's 1/2 x plus the sine of 2x over 4.
Okay?
Yeah.
And we're taking limits of integration. We can either substitute omega t back into it or just change our limits of integration here. Because this was from 0 to 2 pi over omega. So this would be from, once we did the x substitution, 0 to 2 pi. Yeah. And so we end up with my amplitude divided by omega times pi plus 0. Minus 0 plus 0. Sine of 2 pi is 0, sine of 4 pi is 0. Yeah, go through the line. All right. So this becomes pi a over omega. Now recognize that my average though is that number, that was just my numerator divided by my denominator by what the time in